Welcome to this presentation on slope instability mapping in glacier fore-field environments of the high Valais Alps of Switzerland using advanced differential interferometric synthetic aperture radar DInSAR techniques. I am Nina Jones from Gamma Remote Sensing and will talk you through the following presentation. There is a growing need for mapping and monitoring of slope instabilities in mountainous regions due to rapidly changing environmental and climatic factors, leading to glacier retreat and ice and snow melt in vast regions of the Alps. An example of a glacier retreat can be seen in this animation, which is the result of two orthophotos and shows the Findel Glacier in the high Valais Alps of Switzerland. As the glacier retreats, it exposes previously contained rock masses, which in this case develop into a rockfall, as seen on the left, and a larger sliding complex, as seen on the right. Apart from such debuttressing effects, melting of ice, for example in rock glaciers, can also lead to the progressive development of slope instabilities and failure. These examples nicely highlight the need for extensive mapping and monitoring of the high mountains, which, due to largely remotely located and inaccessible regions, requires the use of remote sensing methods. In the following, I present the application of such methods for instability mapping in the high Valais Alps in Switzerland. This study is part of the Alp Glacier project commissioned by the European Space Agency ESA. It is part of the Alps Regional Initiative and consists of partners from Austria, Switzerland, and France. The principal goal of this project is to enhance the observation capacity and hazard assessment in glacier forefields by studying four main products. These are glacier ice velocities, lake formation, snow cover, and slope instabilities. The use of the Sentinel-1 and Sentinel-2 satellites is analyzed to achieve these goals. Our part at Gamma is to study slope instabilities in this context. We do this using advanced differential interferometric synthetic aperture methods. This includes the generation of differential interferograms, stacking products, as well as time series based on persistent scatterer interferometry. I will describe what these are during the course of this presentation. The Sentinel-1 data covering the high Valais Alps includes data from ascending orbit number 88 and descending orbit number 66 from 2015 until present. Acquisitions every 6 days are given from September 2016 and January 2017. Our test site in the high Valais Alps is located as shown here, in southern Switzerland and bordering on Italy. The area comprises the Matter and Saas valleys, which run roughly north-south and perpendicular to the main Rhone Valley of the Canton Valais. A smaller area of interest within this test site is the region around the Findel Glacier as indicated in the red box on the right, which we will look at in more detail in this presentation. A detailed view of the Findel Glacier region is shown here. We use the Swiss Alti 3D digital elevation model, resampled to a ground resolution of 5 meters as seen on the left. A Google satellite orthophoto view can be seen on the right. The location of the two known instabilities, the rockfall and sliding complex that we saw in the previous animation, are indicated by the black stars. The first method we apply is the processing of Sentinel-1 SAR data to generate differential interferograms. These are generated by combining two SAR acquisitions of different dates to exploit the change in their phase information. This change is displayed as colored fringes on a differential interferogram, reflecting surface displacement during the time interval defined by the two acquisition dates. This is also called the temporal baseline. Here we use the shortest possible baseline, so 6 to 12 days, as well as 24 days temporal baselines. Results of this first processing are shown here for descending orbit. One fringe cycle shows movement of 2.8 centimeters. Generally, images covering summer to early autumn months show better correlation compared to winter and spring images, which is due to snow cover and ice melt during these seasons. Here we show two summer 2020 differential interferograms for 6 and 24 days, which show some differences. Overall, the 24 days differential interferogram is more decorrelated compared to 6 days. This is due to higher rates of changes occurring at the surface during this longer time interval, which Sentinel-1, at a wavelength of 5.6 centimeters, can no longer accurately measure. Additionally, the Findel Glacier slide, as shown by the black arrow, is much more prominent in 24 days. This suggests that this slide moves at velocities that are too low to detect during 6 days only. The next method we applied is stacking, which is an advanced DInSAR technique that combines the unwrapped differential interferograms, whereby random noise and artifacts are removed and true displacement is highlighted. The stacks can be variably defined depending on the required results. Here we perform stacking for all the available images, so all seasons, including decorrelated winter images, all summer images from July to October of all years, and summer images of each year separately. This is done for 6 to 12 and 24 days temporal baselines. Stacking results for descending orbit are overall quite good, with summer stacks showing much better correlation and coherence compared to those of all seasons. A coherence threshold masking out all areas below a coherence of 0.4 is applied to remove noise. Movement is displayed on a scale of plus minus 20 centimeters per year for all summer images and plus minus 30 centimeters per year for summer images of 2020. This is due to higher noise levels as a significantly smaller amount of input images is used and thus less mitigation of random artifacts occurs. Black arrows again indicate the sliding complex on the Findel Glacier. In addition to the differing noise levels between the two shown stacking results, distinct features are visible in the summer stack of all years, both on valley flanks, such as the Findel Glacier slide, as well as in higher mountainous regions, as shown by the white arrow. The results therefore complement those of differential interferograms and better highlight and confirm true surface motion features. The final method we applied is persistent scatterer interferometry, which is also an advanced DInSAR technique that allows the detection of slow movements on the order of millimeters. The technique relies on points that exhibit a temporally stable and high coherence called persistent scatterers. These are often urban areas and man-made structures, as well as bare rock. They can therefore be scarce in mountainous regions where snow cover at high and vegetation at low altitudes leads to frequent decorrelation and loss of coherence. Here we use input images covering the summer months of 2015 to 2020 for this reason. PSI results for ascending and descending orbit are displayed on a scale of plus minus 1 centimeter per year, which already indicates that the method is suited for the detection of slow movements. Coverage is relatively good, with no points in the very high mountain regions and along peaks, as is expected. A few additional things can be noted. First, no points at all are located on glaciers and snowfields, and few are found along the Mata Valley due to low coherence. The village of Zermatt, however, shows a high point density due to the presence of buildings. Second, the Findel Glacier slide is not detected, as indicated by the black arrows. This is because it moves too fast for PSI. And third, a large feature is noted on the eastern flank above the village of Zermatt. This is prominent in PSI, but has not been previously detected in differential interferograms or stacking results. PSI therefore also complements the previous methods and highlights the need for multiple techniques to maximize the revenue of information when analyzing mountainous regions. To actually map slope instabilities, a manual screening of the generated results is performed. Differential interferograms are compared to stacking and PSI results to identify surface movements and distinguish these from other artifacts that may look like surface motion. Mapping is best done in a GIS environment using polygons. In order to also assess hazards of the map features, they are classified into movement type, according to geomorphological features using orthophotos, digital elevation models, and if present field data, and according to their state of activity, which is defined by their displacement rates. A first mapping of features in the Findel Glacier region has been performed, as is shown here. Certain features are clearly visible in differential interferograms and stacking displacement maps, while others cannot be seen in either. The Findel Glacier slide, for example, is visible in stacking, but not in the descending orbit September 2021 differential interferogram shown here. On the other hand, some features in the higher mountainous areas are detected in differential interferograms, but only partly in stacking, where the coherence mask has likely masked them out. When looking at PSI results, all the features in the high mountain areas as well as the Findel Glacier slide are no longer detected, as they clearly move too fast. The large feature above the Mata Valley, however, is distinctly picked up in both ascending and descending orbits. The Google satellite and DEM data can be used for a first classification of the detected features according to their movement type. These likely include rock glaciers, rockfold, sliding complexes, and, in the case of the larger feature above the village of Zermatt, a large slope deformation. A detailed classification, however, has not yet been performed at this stage of the project. The activity state of each feature has additionally not yet been determined. Their occurrence in the different results, however, can give a first indication, where features only visible in PSI have lower velocities and therefore lower activity states, compared to those detected in 6 days differential interferograms and stacking results. So in conclusion, the DInSAR methods presented here are clearly well suited to detect slope instabilities in glacier forefields, despite limitations set by decorrelation and loss of coherence. They form a good basis for manual mapping and classification of features in order to perform a hazard assessment. The outlook of this particular Alp glacier project includes the processing and mapping of 2 additional sites, that's Tal, located in Austria, and Mont Blanc, located in France. Additionally, other remote sensing techniques that do not involve DInSAR may provide more information, particularly on faster moving features. For example, methods such as SAR offset tracking could be employed for this. And with this, I end my presentation and thank you for your attention.